Hey there, welcome back. And we are working on week 6 right in this video, and that's the second part of chapter 3. So chapter 3, part 2. What we're going to be covering tonight are balanced equations and stoichiometry. But stoichiometry is going to have 3 distinct parts to it. Kind of a basic or a simple stoichiometry, limiting reactant or limiting reagent, and percent yield. Okay, so first of all, let's think about balanced equations. So what is a balanced equation? Well, remember our law of conservation of mass. And in the law of conservation of mass, we said that mass can't be created or destroyed, which means that everything on the reactant side of the problem has to also exist on the product side. Okay, so first of all, let me put some examples out there, and we're just going to work through a few. And this is one of those things that's kind of individual. There are some straightforward ways of working them, but most people kind of come across their own methods. And the only way to get really good at balancing equations is to do a lot of them. So do all your homework, do all the recitation problems, maybe even try a few extras. If you're still feeling a little bit lost, definitely come to the recitation session where we'll be practicing them. So let's look at a really simple one. And this is one that you've actually seen me do before. Hydrogen gas plus oxygen gas come together to yield water. Okay, and here I have G's, and here I have an L, and G stands for gas and L stands for liquid. Actually, let me go ahead and come over here and I'll put that on the board. So G stands for gas, S stands for solid, L for liquid, and AQ for aqueous. And if something is aqueous, it's dissolved in water. And we won't do a lot of that in chapter 3, but you will see a lot of it in chapter 4. In fact, most of what we're working with in chapter 4 will be aqueous. Okay, so now let's take a look at what we've got going on here. Oh, excuse me. I've got allergies year round. Okay, so we need to make sure that everything on the reactant side is there on the product side. So on our reactant side right now, we have 2 hydrogen atoms and we have 2 oxygen atoms. And on the product side here, we have 2 hydrogen atoms still, but we only have 1 oxygen atom. So this is what's known as an unbalanced equation because there aren't the same atoms on both sides. Now, a really important thing here is that we can only add complete units. So we can't just add another oxygen over here. We have to add a complete set. Okay, so it's good to do this with something that erases, maybe a pencil. The whiteboard pen works great for that. Okay, so I'm going to put a 2 here. So now I have 2 oxygens and 2 times 2 or 4 hydrogens. And I'll go ahead and kind of there. Okay, okay. Well, now here I have 2 oxygens, so those match, but I only have 2 hydrogens and I now need 4. So if I put a 2 in front of this, now I have 4 hydrogens. And it's always understood to be 1 if there's nothing, but I'm going to go ahead and put a 1 in there. You don't have to. I will assume that you need 1 if you leave it blank. However, sometimes that'll help you once we're doing some mole ratio type things. And actually what I'm going to do now is while we're balancing equations, we're also going to talk about mole ratios. Okay, so a mole ratio, and this is a little bit out of order from what's in your slides, but it's all there. A mole ratio is a ratio of quantities of elements. So in the above problem, okay, so remember, this is going to look like a fraction, but it's going to be a ratio, which means it's not part out of whole, but part to part, or part compared to part. So for example, you can see here that you have 2 hydrogens to 1 oxygen. So a mole ratio for that might be 2 moles of hydrogen to 1 mole of oxygen. Okay, and they could go the other way around. You could write 1 mole of oxygen to 2 moles hydrogen because it's a ratio, so it doesn't matter. Okay, now we can also compare, we have this 2H2 and the 2H2O. So we could also say, well, then we have 2 moles of hydrogen to 2 moles of water. Okay, so we've compared hydrogen to oxygen, hydrogen and oxygen, and hydrogen and water. And now the last possible comparison here is oxygen to water. So that would be 1 mole of oxygen to 2 moles of water. Okay, these are the 3 distinct mole ratios that we can make from this equation. Okay, and you might be saying, why do we care? Well, we're going to use these mole ratios in our stoichiometry later, so it's easy for me to just sort of put them out now, and then you'll recognize them later. Okay, so now let's look at another problem. This is called the Haber process, and we take nitrogen gas plus hydrogen gas, and those come together to yield ammonia. Okay, and so again, we have our reactants and we have our products. And so I'll go ahead and make my list here. Again, it's really important that we remember these terms. Reactants on this side, products on this side. Okay, so here we have 2 nitrogens and 2 hydrogens. And on the product side, we have 1 nitrogen and 3 hydrogens. Okay, so in something like this, now we need to think a little bit as we go. Okay, well, actually that we don't. So let's look at nitrogen first. Here we have 2 nitrogens, and here we have 1 nitrogen. Okay, so let's go ahead and we'll put a 2 in front of our ammonia, and then we'll work through this again. And now we have 2 nitrogens and 2 times 3, or 6 hydrogens. Okay, now my nitrogens match, and that's great. So I come down here and I look here and I see that I have 2 hydrogens and 6 hydrogens. So I need 6 hydrogens on my reactant side. So if I put a 3 in front of my H2 here, that means that I have 3 times 2, or 6 hydrogens. And now I can see that my elements match. I'm going to put a 1 here just because I like to see that. That means to me that I didn't miss anything. I didn't forget to balance it. I know exactly how I balanced it. So now let's take a look at what the mole ratios would be for this equation. Okay, well, we can see that we have 1 mole of nitrogen to compare to 3 moles of hydrogen. And that 1 mole of nitrogen to 2 moles of ammonia. Okay, and then the last mole ratio that we could make here is 3 moles of hydrogen to 2 moles of ammonia. Okay, let's take a look at something that would be more challenging. And the equation that we're going to look at now is C2H5OH plus oxygen gas. And here I'm leaving off my states, and that's okay. In chapter 4, we'll always put the states in, but in this chapter, it's not as much of a big deal. And here we have CO2, carbon dioxide, plus water. So let's say we want to balance this. Now this one is actually significantly more difficult than the other one, in part because you'll see that we have oxygen in every single compound. And so when you're faced with something like this, you have to decide what you're going to balance first. So the first thing I'm going to do is I'm going to make my list. On my reactant side, I have 2 carbons, and I have 5 plus 1, or 6 hydrogens, and then I have 3 oxygens. And on the reactant side, I have 1 carbon, 2 hydrogens, and 1, 2, 3 oxygens. So now I'm going to have to do a lot to get things to balance out here. The first thing that I'm going to do is I'm going to notice here that I have 2 carbons and here I have 1. So the first thing that I'm going to do is I'm going to put a 2 in front of my carbon dioxide. And so now I have 2 carbons, and actually before I start counting things up, let me look at one more thing. Okay, so now I have 2 carbons. Now I want to look also at my hydrogens. I don't want to do my oxygens yet because, again, oxygen's in every single compound, which means that I'm going to do it last. Okay, now here I have 6 hydrogens and 6 hydrogens, and here I only have 2 hydrogens. If I need 6, then I'm going to need a 3 here. All right, now that I've done a couple things, I'm going to start like organizing what I have. So now I have 2 carbons. I have 2 times 2 is 4, plus 3 is 7. Oop, wrong spot. 7 oxygens. And then I have 3 times 2 is 6 hydrogens. Okay, now I say, okay, well, my carbons are done and my hydrogens are done, and that's good. Now let's take a look at the oxygens, and I'm going to go ahead and I'm changing color so that you can see each kind of step here. All right, now here I have 1 oxygen right here. So I have 1 oxygen in my ethanol, and then I'm going to need 6 oxygens. So 1 plus 6 will be that 7. And I have an O2, so I'm going to put a 3 here. And then I'll check, okay, yes, I have 1 oxygen here and 6 oxygens here in my oxygen gas. So now I'm done. And I'll go ahead and put a 1 there just to kind of remind myself that I'm complete. Okay, and here's my final equation. Now, in a problem like this, we have a lot more mole ratios. So let's take a look at what those would be. When you only have 3 compounds or 3 species, you have 3 mole ratios. But when we have 4, we will end up having 6. So the more compounds that you have in your equation, the more mole ratios you could potentially make. So the first one here is 1 mole of ethanol, C2H5OH, to 3 moles of oxygen. And then we have 1 mole of ethanol to 2 moles of carbon dioxide. And you want to make sure when you're coming up with these that you don't duplicate any. Okay, and then we have 1 mole of ethanol, C2H5OH, to 3 moles of water. Okay, so now what I've done is I've compared my first compound to the others, and now I'll look at my oxygen, and I don't need to do ethanol because that's already been done. So then I have 3 moles of oxygen to 2 moles of carbon dioxide, and 3 moles of oxygen to 3 moles of water. And the last ratio here is, and I'm sort of running out of room, but 2 moles of carbon dioxide to 3 moles of water. And in a normal stoichiometry, you won't need all 6, but it's good to see where they come from, to see all those ratios so that it's really easy to make one when you need it. All right, so now let's go ahead and introduce some stoichiometry. Okay, now in the slides and the annotations, there's a really, really great template. Okay, so you're going to want to kind of write that template down on a piece of paper somewhere and keep it right there next to you so that you can refer back to it on a test or while doing your homework. So let's take a look at a problem that's in here. Okay, so first of all, we have P4, okay, so one form of elemental phosphorus is basically 4 phosphorus atoms stuck together, plus oxygen gas, and that will yield diphosphorus pentoxide. Okay, now my first step is going to be to balance this. So I'm going to just sort of look at this and I'm going to see that here I have P4 and here I have P2. So I know that if I put a 2 here in front of the P2O5, now I have 4 phosphoruses and 4 phosphoruses. And then I say 2 times 5 is 10, so I have 10 oxygens. And I need 10 oxygens here, so I'll just put a 5. 5 times 2 is 10 oxygens. So now I'm balanced. So your first step is always, always, always going to be to come up with a balanced equation. All right, now let's say that we have, I'm going to change this so that it's a little bit different than what you have in your slides, just so that you can see different examples of that. So let's take a look at this and let's actually work this one backwards from what's in the slide so that you can see that a little bit. Let's say that we want to make 100 grams of P2O5. How much phosphorus will we start with? Okay, and so this is just basically, it's a stoichiometry that's a little bit backwards for what's in the slides. And I wanted to do that just so that you could see it going in different directions. Okay, and again, these are just to supplement the slides. We're not going to do everything in the slides. You can read those and watch those videos, and that will help as well. Okay, so what I'm going to do is I'm going to come over here and I'm going to sort of make some notes on here. So I see that I have 100 grams of P2O5, so I'm going to write that right here. That's my known or my given. It's the thing I'm given in here, so that's what I'll start with because that's what I have. Then it says how much phosphorus will we start with? So that I know that what I'm searching for are grams of P4. Now the next thing that I'm going to do is I'm going to find some molar masses. Okay, so I'm going to determine a molar mass for P4 and a molar mass for P2O5. And I have my handy dandy periodic table here and my calculator. And so I say 4 times 30.974. So at this point, you've probably done quite a few of these and you can start doing them. I don't need to show all of them on the board. Okay. So that means that my phosphorus is 123.896 grams per mole. And then I come over here to my P2O5, and that's 2 phosphoruses, so 2 times 30.974 plus 5 oxygens. 5 times 15.999. And what I get here is 141.943 grams per mole. Okay, so now let's go ahead and start our stoichiometry. The first thing in our stoichiometry is our given. And this is the template that is in, or similar at least to the template that is in the slides. So that's 100 grams P2O5. And you'll notice that I'm writing out the whole thing, okay? One of the big things that I see students doing is not writing out the whole thing. And the problem with that is that sometimes they end up going the wrong way. So I recommend that you, when I say write out the whole thing, I mean to use all of your units. So grams P2O5 or moles P2O5. And that's going to help you not get lost. The next thing in here is going to be the molar mass of your given. But we have grams on the top here, so we need grams P2O5 on the bottom going to 1 mole of P2O5. And that's where we put our molar mass. So this will be 141.943. Now, the next piece in here is my mole ratio, and it's always unknown over known, or unknown over given. And what that means is that since I'm trying to find my P4, oh, you know what? I'm going to put a 1 right here so that I can finish it. Usually I do that, but that'll make this a little easier. So my unknown is going to go on the top, and I see a 1 here, that coefficient in front of the P4. So there I'll put a 1 mole of P4 and over my given. And here I have 2 moles of P2O5 in my products, and so that'll go on the bottom. And now the last piece here is going to be the molar mass of my unknown. Okay. Now here I have moles of P4 on the top, so I need moles P4 on the bottom. And this is also that I can cancel out my units. And I found that the molar mass of my unknown is 123.896 grams P4 per mole P4. All right, now before I do any math, let's make sure that I can cancel my units. And here I can see grams of P2O5 and grams P2O5, so those cancel. And then I see moles P2O5 and moles P2O5, and those cancel. And then I have moles P4 and moles P4, and those cancel. And I'm left with grams of P4, which is exactly what I was looking for. So that means that I've done this correctly. So now what I need to do is I need to do my calculation. And the way this is that I'm going to do this is I ignore all the ones, and I start by saying 100 times 123.896. Okay. I wouldn't normally do everything, but I'll go ahead and show it all so that you guys can see it. So this is 12389.6 on the top. And now on the bottom, again, I'm just going to ignore my ones, and I'm going to say 141.943 times 2. Okay. And then I have 283.886 on the bottom. And now I can finish this by doing 12,389.6 divided by 283.886. And now I'm going to take a step out and see that I have 1, 2, 3, 4 significant figures. And so I can have 4 significant figures. And my calculator gives me 43.64287. And I can have 4 significant figures, which means, and the 2 will round down. So this becomes 43.64 grams of P4. And that is my final answer. And that is what we call simple or straightforward stoichiometry. Okay. Now, the next thing that we want to look at is limiting reactant stoichiometry. Now, if you're watching videos, you're going to see this referred to as limiting reactant, or sometimes limiting reagent. Okay, what's the difference? Nothing. Okay, a reactant is a reactant in an equation. And sometimes people use the term reagent in the lab to specifically mean the things that you're working with. Okay, so if you're doing a chemical equation, you would refer to the reactants as the reactants. But if you're in the lab, which is why we would do all this in the first place, we wouldn't do this math just to do this math. We would do this math to work something in the lab. Then in the lab, they're often called reagents. But limiting reactant, limiting reagent, they mean the same thing. Okay, so a limiting reactant and a limiting reagent basically exist when we don't have enough of one thing to react fully with our other reactant. Okay, so let's imagine that we're working with A plus 3B yields 2C. Okay, this is just an example. That means for every A, and let me go ahead actually, and I'm going to color code these. For every A, we need 3 of our B's. So now let's take a look at, imagine here that we have a chamber. And I'm just going to draw a few of these. Here we have another A, and here we have another A, and here we have an A. Okay. And then some B's. 1, 2, 3, 4. All right, now let's see. So it looks like, wow, we have a lot of B and not much A. But you can't just look at it and say, oh, well, clearly we don't have enough A. Let's take a look at what we could make with this. So one thing that I see here is, here's 1A and 3 B's. Okay, and now let's look here. I have 1A and 3 B's. And here I have 1A and 3 B's. Okay, now see how I have 1 B here and 1 A here? So what that means is that, remember, we need 3 of our little blue B's here to react with this, and we don't have it. Because we don't have enough of that, then we would say that A is limiting. Oh, sorry. We don't have enough of our B values. Okay, so we have this A value, but we don't have enough of our B values. Okay, because we don't have, we need these 2 B values in order to react with this A, but they're not there. So B is limiting. And because we don't have enough B, then that means that A is in excess. So it's one thing to be able to see it in pictures, okay? And you might see this in pictures in your homework and stuff like that. But let's take a look at what that might look like in stoichiometry, okay? So let's say that we have the reaction methane plus water yields hydrogen and carbon monoxide. Okay, so again, we have stuff in various places here. So let's take a look at what we have. Okay. Okay, so here we have 1 carbon and 1 carbon. Okay, here we have 4, 5, 6. So we have 6 hydrogens here and 2 hydrogens here. So let's see if we do a 3 here. Now I have 6 hydrogens and 6 hydrogens. And I have 1 oxygen in my water and 1 oxygen in my carbon monoxide. So actually I'm done. That was all that it took to balance this one. Okay, now let's imagine that we have, actually, this is not a good example because it's not going to be quite what I'm looking for. Okay, I have a better example here. Okay, let's take a look at another possibility, and that's that we have P4 solid plus, and I'm going to go ahead and put the whole balanced equation up right away, will yield 4 PF3. Okay, so P4 solid plus 6 F2, that's fluorine gas. Don't want a dot there. 6 molecules of fluorine gas yields 4 moles of phosphorus trifluoride, PF3. Okay, so then I'm going to put a 1 right here so that we have our ratios. Okay, now there's 2 different ways of doing this. I'm going to go ahead and show you both ways because I can, because it's a video. So first of all, here's the approved method, and I'm going to go ahead and not actually write out a problem. I'll just sort of put everything in here. Okay, let's say that we have 20 grams of P4 and 21 grams of fluorine. And I want to know, well, you need to know which one's limiting and which one's in excess in order to do the problem. Okay, so what you can do first then is let's say, okay, well, let's look at our P4. And we had found on the previous one that the molar mass of our P4 was 123.88 grams, okay? And we had found, and then to find the mass of my fluorine, I need my periodic table, and it's 2 fluorine, so it's 18.998 times 2, okay? So that means that the molar mass of our fluorine is 37.996 grams per mole. Okay. All right, so now let's take a look. So step 1 is to determine moles of each. So determine our moles of each reactant. Okay, so first of all, we have 20 grams of P4. And now when we're going from grams to moles, then we have 123.88 grams per mole. So then we say 20 divided by 123.88. Okay, and what we have here is 0.1614. I'll go ahead and go that far for now. And that's moles of P4. Okay, and now let's do this for our fluorine. And here we have 21 grams of our fluorine. And fluorine is 37.996 grams per mole. Okay. And here I have 0.5527 moles. Okay. And now what we need to do is we need to compare the moles that we have. Okay. We need a 1:6 ratio of phosphorus to fluorine. Okay. And so we have to look at this and say, is our fluorine 6 times greater than our phosphorus? And it's not. We have 0.16 moles of phosphorus and 0.55. So we actually have quite a few more moles of fluorine than our phosphorus, but it's not enough. It's not a full 6 more. Okay, so what that means is that this is limiting. And our P4 is in excess. So using this method, our step 2 here is to do stoichiometry with moles. Okay, so do stoichiometry with moles of our limiting reactant. So I say, okay, then that means that I take this 0.5527 moles of fluorine gas. Now I'm going from here, so I don't need the molar mass again because this was the first part of my stoichiometry. Okay, so now what I would go on with is my mole ratio, and that's 6 moles of fluorine gas to 4 moles of PF3. And last but not least, now I would need a molar mass of my unknown, and that's for PF3. Okay, so I find 3 fluorines, so 3 times 18.998 equals plus 1 phosphorus, 30.974. And that's 87.968 grams of PF3. And now I can do my stoichiometry. So I've got the 87.968 on my calculator. So I'm just gonna keep going with that. So I take that and I multiply it by 4 and by 0.5527. And then I divide that by this 6 on the bottom. And I get 32.4, because I can only have 3 significant figures, 32.4 grams of PF3. And that's my answer. So that's kind of the approved method. The approved method, I have found that maybe half of the students always get, and half of the students struggle with a little bit, mainly because there's a lot of this, try this, then try this, you know, how do they compare? And it was a while ago, actually, that I had a high school student in my class. No, not a high, I got rid of it. I didn't intend to do that. I had a student in my class who came to me, he wasn't in high school anymore, but he says, in my high school class, we did this. And I thought, wow, actually, that worked really, really well. So let me go ahead and put this back on the board, and I will show you their method. And it was if I can find the equation, because I didn't have it written down. All right, 1 mole of P4 plus 5 moles of oxygen gas yields 2 moles of diphosphorus pentoxide, and that's a solid. Okay, so now if we remember from the other page, we had 20 moles of grams of our P4, and we had 21 grams, and that is still not the right one. I sincerely apologize for writing this incorrectly. That was 6 moles of F2 and 4 moles of PF3. And I'm just to redo it. I just want to be able to show the same problem. Okay, again, I apologize for the chaos on the screen. Okay, so the other method for doing limiting reactant stoichiometry is to just do it twice. Do stoichiometry twice. Once with each reactant. So I might start and say, okay, well, I have 20 grams of P4, and the next thing that I need there is a molar mass. And I think that was 120. Now I don't remember. Okay, 30.974 times 4 is 123.896. I had 88 on the other screen, I think. I must just have been pulling from 2 different periodic tables. The 88 was in old notes, but we'll use this one. And because we only have 3 significant figures, we'll end up getting the same answer. Okay, and that is the molar mass of my P4. And the next thing that I need is a mole ratio. Okay, and here I have 1 mole of P4 to 4 moles of PF3. And then I need a molar mass of my PF3. And I have to find that again because I erased it and I didn't write it down. Okay, so fluorine 18.998 times 3 plus my phosphorus 30.974, and I have 87.968 grams of PF3. Okay, so now I work through this, and I have 20 times 4 times 87.968 equals, and then I divide that by 123.896. And I get 56.8 grams of PF3. Great, okay. Now I do the stoichiometry again with my other reactant. Okay, so that's 21 grams of fluorine gas times, okay, now this is going to be the molar mass of my fluorine, 18.998 times 2. So here I would have 37.996 grams of fluorine per mole fluorine. And then I need a mole ratio, and here I have 6 moles of fluorine. And now you'll find that the rest of this is exactly the same, and that's what makes this quicker in some ways than the other one, is that you don't have, you're really only doing this like 1.5 times, because we're going to fill in the same information that we had up above, because we're going to the same unknown. And I'm actually going to mark this here, unknown, just to help you see that. Okay. So now let's take a look at what this would be. So I have 21 times 4 times 87.968. And now on my calculator, I have to put divided by 37.996 equals, and then divided by 6. And the answer that I get here is the same answer that I had on the other board, 32.4 grams of PF3. Now, if you're using this method, you'll see that you have two answers. And the key here is which one do you pick? Well, we always pick our lower value. So this is the answer. This is our product. And this is our limiting reagent. And you might say, well, how do I know that? Well, if I have plenty of phosphorus, I can make 32.4 grams with my fluorine. If I have plenty of fluorine, I can make 56.8 grams of my PF3 from 20 grams of phosphorus. I can't make 56, that's impossible. I only have enough fluorine to make 32.4 grams. So because I only have enough fluorine to make 32.4 grams, that's the most I can make. Okay, and then you could come over here and you can say that the P4 is what's in excess. Another way to look at that is sort of the law of conservation of mass again. See here we have 20 grams and 21 grams. So we only have 41 grams in our reactants. We couldn't possibly make 56.8 grams. That would be impossible. So that's another way of knowing that we must pick this one for our product because we can't make more than the mass that we started with. Okay, I know that this is getting really long and I apologize. I've got one more topic and then we are done with chapter 3. Okay, so let's take a look at another problem. Okay, and that is percent yield. So what is percent yield? It's messy, that's what it is. Percent yield. Percent yield is how much we actually make in the lab. I like to compare this to baking cookies. So when you're looking at a recipe for cookies, it might say you're going to make 4 dozen, or it might say some ridiculous thing. You're like, you're going to make 7 dozen cookies. And you know that there is no way that that recipe is going to make that many cookies. I don't think I have ever, even when working with like a cookie press, I don't think I have ever actually made the number of cookies that they say that I should be able to make because their cookies are really, really tiny, I guess. I don't know. Anyway, so that's sort of like a percent yield. So if my recipe says I can make 4 dozen, but I can only make 3 dozen, then my percent yield is 75%. I can only make 75% of what I'm supposed to make. Okay, so now what we find is that we have a couple of things to determine. Okay, the percent yield is going to be how much we actually make in the lab as a percent. So we have a couple of things to determine here. Actual yield is what we actually make in the lab. A theoretical yield is what we expect to make using stoichiometry. Okay, so let's take a look at a potential here. Okay, so let's say, okay, let me give you a formula real quick. Actual yield over theoretical yield times 100% is equal to your percent yield. Okay, we'll use this in a minute. Okay, So let's say that what we're working with here is CH4 plus H2O, and we had balanced this one before. It makes 3 H2 and 1 CO. And I'm going to put a 1 here and here as well. Okay. Let's say that we are starting with 12 grams of CH4. And we know that this has a 97% yield. Okay, so let's say how much hydrogen are we going to make? Okay, so step 1 in this case is to find our theoretical yield. And we do that with stoichiometry. So we start here with 12 grams of CH4. And now remember that the next thing that we need is the molar mass of methane. So I grab my periodic table and I say 4 times 1.008 plus 12.011. And I have 16.043 grams of CH4 per mole. Okay, so based on that, now I have a mole ratio, and I have 1 mole of methane, and I have 3 moles of hydrogen gas in my equation. And then the last piece in my stoichiometry is always a molar mass for my unknown, 1.008 times 2. Okay, and so it's 2.016 grams of hydrogen per mole hydrogen. Okay, now I do my calculation. So I have 12 times 3 times 1. Okay, 36. Okay, now divided by 16. Oh, goodness gracious. I thought that looked wrong. This is upside down, guys. It's always good to take a look and check when you're going too quickly. Okay, I need to be able to cancel, so the moles H2 need to go on the bottom. And that was 2.016 grams H2. I even thought something was wrong with it and barreled through, which clearly means that I need to slow down. Okay, 12 times 3 times 2.016 divided by 16.043. And what this gives me, I can have 3 significant figures. So I have 4.52 grams of hydrogen. This is my theoretical yield. It's what I expect to make from my stoichiometry. I have 97% yield. So my step 2 in this case, okay, is to find my actual yield. And I'm going to do that using the equation. That actual yield over 4.52 over that theoretical yield times 100 is equal to 97.0% yield. Now, if I were to do the math for this, what I would end up with is that actual yield is equal to 4.52 times 0.97. I can have 3 significant figures, so this rounds to 4.39 grams of hydrogen. And that is my final answer and my actual yield. Okay, it's been a long video, so I'm going to go ahead and stop there. This ends with a very challenging problem that works its way back from what we need to produce, and that's in the slides and the annotations. So make sure that you study that, and we'll practice more of these in recitation.